lectures we've got, we'll be introducing Christian in a moment, but I think they're running 6 consecutive Tuesday evenings, all at 7 o'clock. Next week, we have Tim Budden, who's one of our newly appointed scientists, who's talking about targeting oral fibroblasts and head and neck cancer prevention. The following week, we're breaking a little with tradition, and we've got a speaker from outside Liverpool. We've got Vin Poliri from the Marsden, who's got not only a clinical interest, but research programs in head and neck cancer recurrence, and he's going to talk to us about that. On the 3rd of December, we're opening the doors to public health, and we have become aware of some fairly concerning data about head and neck cancer mortality in our region in Mersey and Cheshire. And so we've asked Yvonne Daly and Deb Moore to present that data, which is actually quite compelling and is going to prompt some action, I think. Followed by that, we've got Jason, who's going to speak to us, and I haven't got the title on this slide, but I'm sure he has. So I'll fill in those details as they come. And on the 17th of December, just before Christmas, Dr. Rachel Brooker, also from Clatterbridge, and myself, we're going to talk about what's new in radiotherapy. So let me just share to introduce Christian. You're probably just about to see Christian in the flesh. But Christian Ottensmeier is a professor of medical oncology, and he's known to many of you already, I know. But Christian joined us a few years ago from having initially qualified in Germany in Munster. I never told you, Christian, I've been to Munster. I've been to the university. My first ever international paper was presented there. Nice place. And I then moved on through the very prestigious Dana-Farber and worked up through the academic ranks in Southampton. And for some reason, we managed to recruit him to Liverpool. I'm going to say I've lost track, 2020?
2020, yeah.
Yeah. And Christian is a medical oncologist. And I thought for those of you who aren't medical professionals and in and amongst this, I'd explain what that means, because medical oncologists are basically involved in drug treatment of cancers. And, you know, I'm a head and neck surgeon, and we also have clinical oncologists who are also involved in the medical treatment. So how does this work? Well, the way in which our specialties work in the UK isn't the same quite all over the world. But I think the way in head and neck things world is usually we don't have this privilege of having a medical oncologist or even more than one medical oncologist on our team. What often would happen is standard of care medical oncology treatment, chemotherapy and immuno-oncology would be given by a clinical oncologist. So what's the role of Christian and his colleagues in medical oncology? And in fact, they've made a new appointment, I've heard this week. It's basically in translational research, early phase trials, and developing and pushing at the margins of what's possible. So Christian's passion has always been immunology, and his practice and his research recently has been in immuno-oncology and tumor vaccines. And in this area, I think it's fair to say in head and neck, Christian is preeminent globally. So it's an absolute privilege for us to have him on board. And without waffling too much, I've used the time to 7 minutes past 7. So I'm going to stop sharing and hand over to Christian.
Thank you. You're super kind. It's a bit embarrassing because I don't think I'll be able to live up to this. We'll try. So thank you so much for inviting me to speak. Can you see, are the slides full screen?
No.
So Christian, we've got your reviewer. So is it switch screen? That's it. Perfect. Thank you.
Great. So I'm a little bit of an odd beast because I've been interested in cancer immunology and particularly cancer vaccines for a very long time, and indeed even during the period of my PhD, so in times in the very distant past, I was interested in trying to understand whether you could make cancer vaccines attack cancer cells or train the immune system to recognize cancer cells. And I still remember vividly sitting in front of a Cancer Research UK grant funding panel in 2011, at the beginning of 2011, and they told me, well, this whole immunotherapy malarkey clearly will not work, and it's all completely useless. And what is the evidence that this can actually do something useful for patients? And then in the summer of that year, the first big study that identified a drug called ipilimumab, an anti-CTLA-4 antibody, shorthand an immune checkpoint inhibitor, for the first time demonstrated that you could actually successfully treat patients with metastatic melanoma. And in the intervening 13 years, immunotherapy has become an integral part of how we think about treating patients, initially with metastatic and advanced or recurrent cancer, but increasingly ever earlier in the setting of being diagnosed with cancer, and now increasingly even before we use surgery or other systemic treatments for the treatment of their malignancy. So this is a change in the way we think about the treatment of cancer that is almost unprecedented. And it's been an enormously exciting journey to be part of this and to be able to offer this kind of stuff to my patients. What we're seeing now is that cancer vaccines are beginning to play a role as an adjunct to the things that we are using in terms of systemic treatments as well as local treatments for cancers. And I'll tell you a little bit about the principles and then some worked examples, and then finish on what we are up to here in Liverpool, particularly in the Head and Neck Center. So if you think about the human immune system, then it is a system that we all have, and it aims to protect us against a foreign challenge from bacteria and viruses. The immune system is really good at picking up what is new and what is different. So, for example, along comes a flu virus and infects you. That looks really different to the immune system. So the immune system sees that change and then eliminates the cells that are infected by the virus. So the key message here is change that's quick is good for the immune system to pick up. Cancer, however, grows often very slowly and often over many years, and that is much harder for the immune system to pick up. And so then if you have cancer, or if the cancer has come back after treatment, then we know already that the immune system must have failed at least once to recognize this malignancy. And so then if you turn cancer immunotherapy into a clinical question, or maybe an immunological question, this becomes, can we re-establish immune control? Can we turn this failure into a clinical success? To understand that, you need to know that the immune system is normally all about immune suppression. The whole system is geared up to dampen things down, because it's really not a great thing if your immune system is active all the time. So when you have your virus infection, there's a boost of activation and then a gradual resetting to calmness. And this is what cancer subsumes. So it doesn't really invent any new biology. It just uses existing methods that our immune system has to calm things down. But in this case, not to calm down an overactive infection response, but to protect the cancer cells that are being picked up by the immune system. And so immune control then is to switch this over, and to enable immune control, you need a group of cytotoxic or killer T cells. They're T cells because they grow in the thymus, and they go into the tumor, recognize the cancer cells, and then clear the tumor. And if that is successful, then you can achieve cure. And this has become standard of care in many solid tumors. And I've just made a list on the right. So melanoma, bladder cancer, lung cancer, hepatocellular cancer, head and neck cancer, and so on, and so on. And by and large, across most tumor types, with drugs that are of this sort of pot, these immune checkpoint inhibitors, we make about between 10 and 25% of patients better. And making better means that many of these patients live disease-free and are actually given their life back. So from an oncologist perspective, this is an exhilarating change, but is also an enormous pressure. How can you turn this into benefit for more patients rather than the small minority? And we know that one of the keys for this is to combine these checkpoint inhibitors, these anti-PD-1 antibodies, with other drugs. For example, types from this class and this class together in melanoma lead to a cure rate about 50%. We know that the effector cells, the cells that protect us against the cancers, are T cells. T cells because they're coming out of the thymus, and I'll come back to that a little bit later with the graphic. And these cells sit in the tumor. And this is data from head and neck cancer. And it's from the time in Southampton. This is on N of 544. And at the beginning, at diagnosis, everybody's alive. And then as time goes on, patients die. And that's why these curves drop down. There are blue curves and black curves. The blue curves represent patients who have a head and neck cancer type that is driven by a virus that is called human papillomavirus. And then the black ones are the tumors that are not caused by virus, that are caused by smoking or alcohol abuse. And you can see that these black curves, by and large, lie under the blue curves. And that means that the patients do less well. And roughly half of the patients die overall from this HPV negative tumor. What is really different, though, is that in the tumors that are doing really well, there are many more of these protective T cells, or because they're tumor infiltrating and they belong to a group called lymphocytes or white blood cells. These tumor infiltrating lymphocytes, when they're abundant, are really protective, and the patients who have those do well. And the tumors that are HPV negative and that don't have many of the T cells do much less well. So this is, I think, evidence that the T cells, even if they're just occurring spontaneously, are protective. They're quite simple to figure out. So here at the bottom is a group of is a non-lung cancer, actually, where there aren't very many T cells, and the T cells are picked out in brown against the backdrop of the blue cells that are all the tumor cells. And you can see there are a few brown dots in this patient, and there are tons of brown dots in this patient. So this patient here would fall into this category here. So it's relatively easy to figure out which group an individual patient belongs to. And so if these brown dotted cells are abundant, then you get patients with good outcome, because ultimately the immune cells are able to contribute to protection against the cancer cells. So then if we come back to immunotherapy and why it often doesn't work, then one really important reason is there simply aren't enough of these T cells. So these cases here, where the drugs that we currently use don't work so well, and they don't work so well because there aren't very many T cells in the tumor. And so then the obvious correlate from that is, if there aren't enough T cells, how can you get to are there more T cells? So to turn this kind of setting into this kind of setting. In other words, how can we overcome the failure of not enough immune cells? It turns out that that's relatively straightforward, and that is using cancer vaccines. So vaccines, you all know from the COVID era is an approach, a medicine that you give to the patient, either into the muscle or inhaled or intravenously, that trains the immune system what to look for. And this training leads to new T cells, initially in the lymph glands and then in the blood, and then eventually they wander off to the tumor. And that's what we are trying to achieve with cancer vaccines. Now, in order to understand all the issues about cancer vaccines, you need to learn a little bit about how T cells work. So T cells are called T cells because they are trained in the gland called the thymus. So this is a soft tissue gland that sits behind the breastbone and in front of our main airway. So this is a little bit like going to school. So the T cells are born in the bone marrow, so the central part of our bones. They go, they walk to school. They go into the bloodstream. They sit at the bench in school in the thymus, and they're trained against a curriculum. And when they finish school, they're allowed to go into the blood and do their day job and essentially graduate. Now, passing the A level has to fulfill two conditions. One is they must be able to react to stuff that is around, so they can't just be sleepy. And the second is they must not recognize stuff that is in the curriculum as belonging to our healthy structures. So this conceptually is labeled as self. So the cells that are not recognizing self and that they are able to recognize foreign stuff, they're allowed to go into the blood. So these are the cells that then will protect us against flu or CMV, but also against cancer. But the rub is that cancer cells are about 95% self. So there are only small differences, and these differences often develop over long periods of time. So therein lies a dilemma. But what I've just showed you also is that even in cancers that do develop in humans, there are still individual patients, these HPV positive T cell rich tumors, that nonetheless are able to train immune cells and attract immune cells sufficiently well for them to be useful. So if we then put all of these things together, then once the T cells have left the thymus and have been trained to not recognize self, there are then various options of what they might find interesting and that might, for example, be in the tumor cells. And there are molecules that are found upregulated more of in the cancer cells that are also found to low quantities in healthy cells. There are molecules that are genuinely unique and new to the immune system, like the viruses that cause these HPV positive tumors, oncoviral antigens. And then there are molecules that are the product of the cancer cells becoming cancerous in the first place. And for that, you need to understand that cancer cells are different because they damage the genetic information in the cancer cells. And these differences can become visible to the immune system. So almost as though the stuff that is enabling the cancer to become possible also becomes an Achilles heel for the immune system to recognize. And these are the molecules that we take advantage of when you think about making cancer vaccines. So the process is relatively simple. You read out what makes a cancer cell different from healthy cells. And we can do that in the test tube now relatively quickly and in great detail. You take that difference and turn it into a vaccine, and then you give that to the patient, and then you hope for the best. And I'll hopefully show you some evidence that this can actually be useful. And then if you think about it, you could make either one vaccine for each individual patient. If you make a new vaccine that is based on what is unique for that cancer in that human being, and I'll show you some evidence that that is practically possible. But you could also do something that is a little bit less complicated. You could make one vaccine for lots of patients and use the same product in many people. So this would be more along the lines of stratified medicine rather than personalized medicine. And clearly, if you had a large supply of a particular cancer vaccine on the shelf and you could pick out the patients who would benefit, then you would be on for a winner. So this staggering thing is that cancer vaccines suddenly have burst into mainstream oncology. And this all happened at the end of 2023, when the same company that made the mRNA vaccine for COVID presented their first data in melanoma, where they had made a new vaccine for each patient and were giving that in patients who had resected melanoma. The field is moving almost, there's a new product that looks promising on a monthly basis now. And we've become much better at making vaccines. We know more about when to give them and who to give them to. And we also know what we should add to the vaccines to turn vaccines into something clinically useful. So the concept that made this, the oncologists and the immunology world sit up and listen was that you would be able to take a tumor sample, say, take this metastasis from the liver, and read out all the differences that the cancer cells have to the healthy cells. So, for example, white blood cells. These are these PBMCs, white blood cells taken from a blood draw. And you read out the differences, and you then can turn that into a sort of string of beads, where each little box here is one particular difference in that individual patient. And then you can turn that into a vaccine and give it to the patient. And that's what we've done in our first study here in Liverpool with a company called Transgene. This was in patients whose head and neck cancer was at very high risk of coming back. They had completed their surgery and they had completed chemoradiotherapy, so all the standard of care treatment. And then we asked the patients to allow us to either give them a vaccine that we'd made for them, or to randomly follow them only and have the vaccine kept in the fridge for a rainy day. And really quite unexpectedly, none of the patients who have been vaccinated have relapsed. and there were 16 in that initial group, and about 20% of the patients who were not vaccinated did relapse. And this is now moving into a larger study that we're participating in, again here in Liverpool, which we are leading in the UK. There are a number of 6 other UK centers now and 10 French centers. We're really trying to demonstrate that this is useful. And it's the only and the first example where a vaccine of its own and on its own, without any further ado, can seem to be able to make outcomes better. In our own program of work, and this is work that I do collaboratively with Professor Natalia Sevelieva, who's done all the heavy lifting in the laboratory, we're going to try and take this approach into patients with lung cancer who are offered standard immunotherapy, and we're going to try and add our personalized vaccine to the standard immunotherapy. Because I think that in advanced cancer, you need this kind of combination to be useful. And we're going to use a different platform, not a virus as in the previous trial, but a DNA vaccine. So Professor Savalieva and I both come out of a laboratory that was very interested in developing DNA vaccines. And we've been pursuing this area of investigation, this strategy for almost 20 years now. So it's absolutely amazing that we'll be taking this kind of personalized vaccine construct and concept into the clinic in Liverpool. Here are the data from Moderna that set the world alight. So this was a vaccine in melanoma patients, where normally we would clear about half of the patients with standard immunotherapy after surgery, and adding the vaccine made a big difference, and added another 50% of cure rates to those patients. And the data have been now followed up for almost 3.5 years and still look good. And lots of group are in this space. So DNA, for example, that's a group in Norway called NICODE. Of course, you will know about BioNTech and Moderna, I've already mentioned. Transgene, Geneos, they're all working in this space and trying to come up with the best recipe or the best mix of components to make the vaccines work really well. And this has led to an enormous effort in the UK, led through the Department of Health, who made a very large agreement with both Moderna and BioNTech to really support the portfolio of trials that these two companies were developing, and reaching out into many centers, even where the trials weren't running, to enable patients to move from place A to place B to participate in these kinds of trials. And that's called the Cancer Vaccine Launchpad. And that's not just for trials with Moderna BioNTech, but for across the board. So our own starting point will be these personalized vaccines, but both Natalia and I have this privilege of having thought about this problem for a long time. And we think that some of these molecules that are off the shelf and could be used against multiple patients would be a really good way of going. And we have 2 molecules of this flavor. One is called MAGE-D4B, and we've been able to show that it is very widely expressed in lung cancer, but also widely expressed in head and neck cancer, and it would be available and useful for patients with bladder cancer. So we're delighted that we're currently collaborating with all places, the Malaysian government and Cancer Research in Malaysia, with whom we actually discovered these molecules on taking this into the clinic for the first time. And we are in the process of waiting for hopefully funding to be agreed that we can take this into patients with non-small cell lung cancer, again in Liverpool, this time in patients who haven't yet had any recurrence, but who are waiting for their cancer to be removed by surgery. And here we're hoping that the vaccine would increase the chance of being cured from their cancer. So the same concept of shared molecules also applies to molecules that are from viruses. So this human papillomavirus. It is an onco because it causes cancer, viral because it comes from human papillomavirus. So an oncoviral antigen. And this is a vaccine that we initially developed with BioNTech well before COVID ever came along. It's called the catchy name BNT113. And we tested this in patients with head and neck cancer and other HPV-driven cancer for the first time. And we've just released our first data in which we can show that it does seem as though even in patients with end-stage disease, we're delaying disease progression. But really excitingly, we're able to show that compared to baseline, where there are very few T cells in the tumor, after vaccination, there were many, many more T cells. And this is an N of 4 because we needed paired biopsies for this. But this clearly establishes that using a vaccine trains the immune system the right way. You find the T cells in the blood, they go into the tumor, and on its own, the vaccine doesn't cure the cancer, because you can see these people still had progressive disease at the end of the day. But I think in combination with an anti-PD-1 antibody, so our standard immunotherapy, this is likely to work really well. And indeed, we've just this week released our first patient out of this trial back into his everyday life, having had 2 years worth of disease. And he had a so-called PET scan, which is the most sophisticated we have looking at cancer, and he's completely disease-free after two years of treatment on this trial. So we're superbly excited that this may be our first worked example where in advanced cancer, vaccines plus standard immunotherapy can make a real difference. And you know, the Modernas of this world are really making very big and ambitious plan. So in lung cancer, head and neck cancer, melanoma, bladder cancer, kidney cancer, and so on, and so is cutaneous cancer of the skin. So in the next 5 years, I think we will have many trials, both commercial and academic, that really probe how well this stuff works in patients, what the exact mixes are that we should use for the vaccine, what should go with the vaccine, and then which tumor types this will be most useful for. So Clutterbridge has done really well, and we've opened a whole raft of trials in Clutterbridge, and particularly I'd like to mention this one here, which is called another BioNTech trial, BNT112, which is in patients with resected colorectal cancer, where Dr. Montezeri, one of our medical oncologists, and Dr. Rob Jones, who's one of our colorectal surgeons and liver surgeons in the Liverpool University hospitals, have really done an amazing job at bringing this trial to fruition and delivering patients into it. And you can see we're quite heavy in our interaction with BioNTech, but we're working with a whole range of other partners on developing cancer vaccines with Scancell, another UK study, Moderna and Merck, Cancer Research UK, Durance is a commercial trial, and then these are our own DNA vaccine trials. So cancer vaccines in the clinic then. I think that we still need to define the best vaccine target and the best vaccine delivery method. But I think these drugs are here to stay. And I can see that I will still be clinically active when we'll be making decisions about who to give an immunotherapy alone, who to give a cancer vaccine alone, who to give both together, and what else we might need to have to give with these vaccines. And I think these drugs will sit on the shelf and will be part of our standard oncology armamentarium. So back to the Cancer Research UK program grant review in 2011, they were clearly wrong. And I'm so glad that we stuck with it and are now really beginning to see how these kinds of approaches make a difference to real people with real cancer. With that, I'd like to close and thank lots of people that we are privileged to work with. The people in my own lab, of course, the team here in Liverpool, Professor Natalia Sabalieva, who's the laboratory scientist who has driven much of this work in the preclinical setting and with whom I've teamed up and with whom I share a lab, and my own team, a lot of amazing clinicians who we work with. Richard is on here, the head neck surgeon in Liverpool, but also the thoracic surgeons here in Liverpool with whom we're doing all this work in lung cancer. The people back in Southampton, a really eminent and highly productive head and neck surgeon in Poole, an amazing group of scientists in the La Jolla Institute for Immunology. I didn't speak much about this today, Vijay Anand and his fellow, who's now a professor at the MD Anderson. Our team that we're collaborating with in Malaysia on the DNA vaccines in head and neck and in lung cancer. And of course, not last but not least, the people who've allowed us to do this and have put the money into the program to allow us to develop this. And I think most of all, the patients who will hopefully be willing to participate and help us develop this stuff further, hopefully for useful clinical outcomes. And with that, I'll open it to any questions.
Thank you very much, Christian. if we go back, so let me just check. Yes, I'm back on. So, Christian, we will take questions. I realised that there are a lot of people, well, that's hardly a surprise, a lot of people who've logged in tonight, and I didn't introduce myself. So I'm Richard Shaw, I'm a head and neck surgeon in Liverpool. And I didn't introduce my background either, but one of the few international head and neck meetings we're hosting in Liverpool in July 16th to the 19th next year, the International Academy of Oral Oncology. We hope to have 1,000 or so oral cancer specialists in Liverpool. So just to let everybody know about the face and the background that appeared at the beginning. Now, back to the important stuff. There are questions. So there's a question from Ivan. So in your opinion, which cancer vaccine approach is more likely to prove successful in the future with the relevance and usage? Personalized mRNA type or something off the shelf or DNA or some other approach? And that merges in with a question I had actually, which was when these neoantigen personalized vaccines hit the market, what sort of price tag are going to be attached to them? Because I think that's two ends of the same question, I think, Christian.
Yeah, so I think for early disease, targeting the neoadjuvants looks really promising, but the cost is high. You need to not only take a sample from the tumor and have enough to make the vaccine from, but you also have to produce it and then deliver it. And roughly the starting point for this is about 100 grand per patient. I think for advanced disease, this will be much more problematic because we know that the primary and the metastases are really different. So which one do you pick for making your vaccine from? And do you have to chase your tail if it doesn't work? So those questions are completely open. I personally believe that there are many other molecules that are shared that have all the same immunological features that neoantigens have. So, a T cell doesn't really care whether the molecule is new. It only cares whether it's encountered it before and whether it's been trained to ignore it. So these molecules that are not undergoing central tolerance, so they're not on the curriculum in the thymus for the T cells as they go to school, include oncolytic include viruses, so HPV I've already mentioned, but there are many other molecules that will fulfill the same immunological criteria. That testing is just beginning because others are also seeing that this is a problem and will have to wait what the direct comparisons will do. So BioNTech, for example, is proactively developing shared antigens. My personal view is that it is likely that there'll be a mixed community that will finally emerge. And it will all be driven by the price. So, a DNA vaccine that's off the shelf, the per vaccine cost will be someone, I don't know, 100 quid, 1,500 quid, something in that ballpark. Whereas a personalized vaccine will be £100,000 per patient. So, it will depend on what we'll be able to afford. And I think more importantly, whether it works. But that is, I think, in my view, pretty clear now.
Yeah, I mean, it's challenging, isn't it? £100,000. Having said that, if you added the cost of all the hospital care, major surgery, chemoradiotherapy together, and we don't cost it very well in the NHS, but if you did add those costs up, it would be towards the same ballpark. It's an interesting thought. Your comments probably address another question which has occurred, which is how frequently do these neoadjuvants of interest cross-react with self and then produce unexpected or serious toxicity? And how is that tackled? Is it a common thing? All of these these neoantigen trials and vaccines, do they generate unexpected toxicities? How do you manage this?
So the overall answer is no, they don't. And I think it is because if they're immunogenic, there will already, as visible to the immune system, there will already be T cells against them. They've just been turned off in the tumor. So adding more T cells of the same flavor, just the vigorous version thereof, is not going to add new toxicity. And that's how the data read out. All the toxicity comes from the add-ons, so the pembrolizumab, rather than from the vaccines. So it looks as though these will be very safe.
So Harish has asked a question. It's why are they vaccines? I think he's asking, why are they called vaccines? Aren't vaccines administered to healthy individuals to prevent a disease and not used to treat people who already have a disease? So I guess he's asking, why isn't there some other category of therapeutic in terms of its branding? Why is it called a vaccine?
Well, because they work like vaccines. The biology is the same, and so that's one. The second is the vaccines are only for prevention of disease rather than treatment of disease. That's a UK special. In the US, there is no such preconception, and in UK law, or rather in regulatory speak, vaccines, these would not be vaccines. These would be personalized immunotherapeutics. But that's a sort of problem that only the UK needs to get their head around. The Europeans, the Americans, and indeed the Asian communities are quite happy to call them vaccines. So for me, the use, I've stuck with the word because I think about the immunological principle and give something that will train T cells in a way that enables the control of disease. Whether that's then preventative or whether that's therapeutic, for me is relatively indifferent. And finally, patients understand what I mean when I say, I'd like to give you a cancer vaccine. There's a sort of an immediacy of the grasp of what I'm telling them. But if I say, I want to give you a personalized immunotherapeutic that is an mRNA that we want to make from your cancer to train immune cells against your cancer, that's much less sort of immediate for people to understand, because everybody knows what vaccines are. And, the explanation of, well, here we're using the same concept for cancer that's already happened is much easier to jump than taking it from a vaccine into an immunotherapeutic. So you're absolutely right, Arish. This is an ongoing area of discussion. The MHRA is really grappling with the labels. I suspect that in the end, the endurance and the ease of use will win. But at the moment, these in the UK are not vaccines.
Now, we'd set you up nicely to answer a question about prevention of cancer, Christian, and you haven't taken it, so I'm going to nudge you, because we've been discussing for quite a while, but there may be an avenue in this field and this approach about prevention of known pre-malignant lesions progressing to cancer. Do you want to speak to that just for a few moments?
Yeah, so there is sort of secondary prevention, cancer not coming back. That's already here. That was what the Moderna trial showed. Then there is, and of course, our own TG4050 study. There's prevention of transformation. So people with high risk of developing cancer with a known pre-malignancy. Oral dysplasia is, of course, the area, Richard, where we're talking and where we would really like to take our vaccines into the clinic. And then there are also some really serious efforts to do this in people who haven't yet got cancer, where you just think they have risk of developing cancer. For example, people with genetic abnormalities, Lynch syndrome, p53 mutations. And the first projects are ongoing to test just that. Because if you could turn those abnormalities into in something that makes T cells recognize the pre-malignant cells, that would be really, really cool. So we'll see. I think this is reality. And then the final piece is people who haven't yet got cancer but are just at high risk, for example, heavy smokers, people who we would put through, for example, lung cancer screening program. Could you pick up people in that setting where you would make a preventive vaccine that would not prevent them from ever getting lung cancer? That's, I think, conceptually also there. We know how one might go about it, but it's just the sheer cost of doing that to tens of thousands of people that is going to be prohibitive. So very much on the radar. I think we'll be talking about this much more, and I think this will also happen.
So a question from Amy. Great talk. Can I ask you, have you considered the way in which you deliver vaccines, i.e. not via syringe, but maybe directly to the oral cavity via a patch, microneedle, whether you think it may improve the penetration into the stroma where the T cells reside? So I think this is a talk about method of delivery, but also the special immunological context of epithelium, which is different. I remember being taught dermatology at medical school to say the stuff that goes through the skin often cause a different reaction to stuff that's exposed to the body in a different way. I think that's what Amy's getting at.
Yes, so site of training immune responses has a big impact on the kind of immune response you get. So Amy, spot on, really well picked. Now, we don't inject the vaccine where the cancer is. We inject it away from the cancer because we want an immune response to be activated in the draining lymph nodes or the immune cells that actually wander to those. So intradermal versus intranasal versus inhaled versus intramuscular versus, and in the case of BioNTech, intravenous, all are being tested, and no one really knows what's the best. Natalia and I have our prejudice of what might be smartest, but no direct side-to-side comparisons have been done. So I think that will also come. We just haven't done it yet. I think at the moment everyone's still waiting for the aha moment. Cancer vaccines work more broadly than just with the Moderna vaccine in the adjuvant setting in melanoma.
And a question from Sarah Jane Ketterer. What's the average time for making the personalized vaccine? Just wondering about this alongside the cost or the logistic aspect.
Currently 12 weeks, with an ambition to cut it down to 6 weeks. But that will depend on capacity, getting the sample to the sequencing hub, doing the sequencing, assigning the neoantigen mutation, then turning that into a vaccine. The quickest is about 12 weeks at the moment.
So 12 weeks is a challenge as a primary treatment, but not as an adjuvant treatment. And that raises a question which is impossible for you to answer in this sort of time interval, but it's about where immuno-oncology treatments, tumor vaccines, sit alongside radiotherapy and surgery, because almost everything you've said assumes standard of care treatments, which tend to be either radiotherapy or surgery or both, are going to continue. So perhaps a slightly kinder question than that ridiculous one would be, will immuno-oncology over the next decades replace people like me and our colleagues in radiotherapy doing all our very toxic things and just be able to make the tumors melt away?
So I tried that on with my opponent being Kevin Harrington, and Kevin slaughtered me. I proposed that yes, that might be the case, and Kevin showed me the error of my ways. It'll all be in the data, won't it? So in lung cancer, we now give a vast or many patients chemo and immunotherapy before surgery. I think the additional vaccines will identify whether that makes a big difference, and then whether you can back away from the chemotherapy. So those trials are coming. I think can immuno-oncology replace surgery? It's not immediately on the horizon, I don't think.
Yeah.
Will it replace radiation treatment? No, but it might be a very good adjunct to radiation treatment. And I think vaccinating before and then vaccinating after chemoradiotherapy looks very promising, and there are a number of trials that suggest that's a good idea. I think that it will depend a little bit on which bit of the body you're irradiating. So, if you're irradiating the whole head and neck and all the lymph nodes are involved, it'll be more difficult for T cells to wander back into that tissue if all the sort of immune environment has been sterilized. But ultimately, we'll need to do the trials and figure that out.
Yeah, I mean, there's some fairly challenging data with the first trials on the standard immuno-oncology agent with radiotherapy, aren't there? That it was basically found to be negative, and I presume you just explained the reason why. Yeah. And you mentioned lung cancer. So we're going to finish tonight with a question from John Field, who's a lung cancer researcher. Looking to the future, developing vaccine for very high-risk individuals identified in targeted lung health check, but no nodules seen on the CT scan, but are still considered to be at very high risk. So it's sort of secondary prevention, sort of high-risk group prevention. Consider a trial with very high-risk individuals based on those risk models. So somebody almost certainly will get lung cancer, but you can't see it yet based on everything we know.
Yes, I think the need will be for a very broad vaccine that would target multiple molecules that the lung cancer cells might potentially upregulate. And we know that biologically that makes sense, because if you look at if you look at dysplasia in the airway, that's rich in T cells. And when you follow dysplasias in the airway, you often find that one area has gone and another one has appeared, then that disappears, and then another one comes up. So there is very good evidence that in the airway, pre-malignant lesions are susceptible to immune attack. It must therefore be likely that if you picked the right vaccine and gave that in people who just have dysplasia but haven't developed malignancy yet, or who on other criteria have very high risk, would benefit from such an approach. The problem is, and we tried this on, John, did we, with Charlie Swanton and his team, that a very large trial would be sort of several thousand patients in the appropriately defined risk groups, and CIUK wasn't keen on funding that because it would be too expensive. I think the time will come. I think this is around the corner, and we should do the trial. Why don't we set it up?
It's one of those things, isn't it? It's also quite hard if there's any toxicities to really consider toxicities in the same context as a patient who's got a cancer with a poor prognosis. It's really difficult to get into that same bracket of risk because the patient and the way it's framed will feel very different with those toxicities. So it's exciting times, Christian, and thanks for very good attendance tonight. Thanks for everybody attending. I was actually just going to apologize to Jason because I didn't mention the title of his talk properly. The title of Jason's talk is, in fact, Santa is Coming to Town, a Modern Healthcare Story. What Jason's going to talk about later on in December is the robot in head and neck surgery. And next week's talk, thanks, Christian, next week's talk is one of our newly appointed scientists. And we've brushed on the area about head and neck cancer prevention today, but more of that. And I think the agenda in cancer care will be increasingly towards prevention. And we've seen the political agenda shift to that, and I think the clinical agenda as well. And so we're delighted that Tim has joined us in Liverpool, and Tim's going to talk about targeting oral fibroblasts in head and neck cancer prevention. But thanks, Christian, you've set us off sailing in completely the right direction with this Red Lecture Theories. You've kept to time. It's 10 to 8. Everybody gets the rest of their Tuesday evenings. Thanks, everybody. I'm going to say good night.
Thank you so much. Goodbye, everybody.
Bye. Bye.